for those of us in the US, good morning. Some of us it's earlier than others. For those of you around the world, thank you so much for joining us. As Paul said, I am Bethany Bray, and I am here this morning in Chicago, Illinois. And I am going to kind of lead us through the material. And then, of course, Stephanie and I together are going to do the lectures, our software demos, walk us through the exercises that are hands-on. And we want to get to know you a little bit over the next 2 days and the work that you're working on. So Stephanie and I both focus a lot of our work in substance use and comorbidities, including mental health and emotion regulation, things like that. But we're very excited to hear about your applications. Welcome, Stephanie. Before I jump into a little orientation to the materials, do you want to give a little welcome?
I just want to say hello. Bethany and I go way, way back. We are colleagues for many years, but we also trained together for some time, and we're also really good friends. And we have a very friendly kind of approach to this material. So we just encourage you to really engage with us, engage with each other, and but with two of us, you'll see us go back and forth a good bit more formally. But what that also means for you is that while one of us is lecturing, the other can be monitoring the Slack channel, the chat window. So we're here. We're really excited to spend this time with you, and very informal. So feel free to turn off your monitor. Feel free to leave it on and grab a snack. Anything goes. So we're really happy to have you. And thanks for the posts in the chat window. Excited to read them.
Yeah.
Okay.
Awesome.
And Bethany is a world-renowned expert in these methods and also M+ syntax for these methods. So we're really fortunate to have her expertise with us today.
But no pressure. No pressure.
No pressure. We are extreme pragmatists. We want this to be really useful for you. That's why we took the time to annotate the M+ output for you of the demonstrated examples. We want to make this as user-friendly as possible. It's so easy to come to a methods intensive workshop and leave and never really put it into action. So if you've got data at hand, and you've done some latent class modeling in the past, or you feel ready to, we encourage you to start working on your own data during this workshop. Please feel free. We want this to be as practical and useful as possible. For us, great outcomes would be that you're fitting models in your data that you didn't know how to fit before today. And also, maybe you're going to write a grant proposal where you're going to propose to use these methods to existing data, so we can help you craft those questions and think about what more you can do with your data. So we really want this to be a win for you in practice, not just in theory.
And with that, I just want to share briefly the agenda, and then we will get started. So just as a very, very, very quick 50,000 foot overview, we are going to do a very brief review of latent class and latent profile analysis, just to make sure we're all on the same page. This is not a workshop about LCA or LPA, so this will be very brief. And then we're going to jump right into latent transition analysis to help you formulate some research questions. Then we'll talk about technical considerations of how you act, things that you need to think about to actually fit these models. And then we'll talk about software options and do a demo so that you can see how to fit these models if you haven't before. And then we'll finish up with a guided practice of exercise 1 of fitting a latent transition model. So with that, I'm going to pull up our slides and all right, so welcome. Stephanie and I already introduced ourselves. We already went over our plans for the next 2 days. So Stephanie, please take it away.
Okay, so again, I'm really happy to have you here. We're going to jump in and do just a quick brush off the cobwebs kind of discussion about LCA and LPA. So LCA, of course, is a latent class analysis. And when we say LCA and the field says LCA, we're typically talking about a static categorical latent variable, the latent class variable. And we're talking about a latent class variable measured with categorical indicators, multiple categorical indicators. If the indicators, the observed variables, are continuous variables, then we would call that model latent profile analysis, or LPA. Just keep that in mind when we talk about LCA and LPA. These models are very, very similar, categorical indicators versus continuous indicators. LTA takes us to the topic of interest today and tomorrow, which is latent transition analysis. In LTA, now our latent class variable, regardless of whether the indicators were continuous or categorical, right? That's the measurement model. You're either doing a latent class or a latent profile model. But once that's modeled, we want to allow for individuals to change in class membership over time. And so now our latent class variable becomes dynamic, and that's latent transition analysis. Great. So what we are going to do first is to just remind us what LCA is and what the parameters are. So LCA, again, the latent construct we're modeling is a categorical latent variable. It presumes that we theorize that individuals can be divided into subgroups, or a population can be divided into subgroups of individuals or units based on some unobservable construct, our latent class variable. The construct of interest is a latent variable, but unlike factor models, in LCA, the unmeasured variable, the latent variable, is categorical. These subgroups are called latent classes, okay? So we also assume that the true class membership is unknown. It's because it can't be observed with a single questionnaire item. What class are you in? Instead, we have to triangulate and infer latent class membership from a set of indicators. So the true class membership is unknown, but we theorize that everybody's in one and exactly one and only one of those latent classes. So the theory posits that the latent classes are mutually exclusive and exhaustive. What that means is there's measurement error. We don't know for sure, truthfully, what class people are in. But because we theorize that they're mutually exclusive and exhaustive, our latent class membership probabilities sum to 100%, right? Okay. So when we fit a latent class model, again, we've got categorical indicators and a latent class variable. We're estimating two sets of parameters. The latent class prevalences, so that's how big the different classes are. For example, what's the probability of membership in a high depression latent class? Those are our latent class prevalences. And then we have our measurement parameters, which we call item response probabilities. So we have categorical indicators, in this case, symptoms of depression, and they map onto our latent class variable. And so an example item response probability would be, and this is shown on the output when you fit these models, one of those probabilities might be, what's the probability of reporting I felt lonely on that item, that response to that item, given that I'm in this particular latent class, say a high depression latent class. So this is LCA in a nutshell. We've got our latent class prevalences and our item response probabilities. Okay, so in this brief kind of empirical example, let's take a moment and think about latent classes of adolescent drinking behavior. These data were, this is a real example from data from 20 years ago, monitoring the future public data. So we have a pretty large sample of 2,500 high school seniors. Our goal is to identify and describe the underlying classes of drinking behavior in this population. And this was an example used for the paper that introduced PROC-LCA years ago. So in this example, we identified drinking classes, excuse me, from a set of 7 binary indicators. Excuse me, Bethany, you can advance. So the indicators of drinking behavior, we have lifetime alcohol use, past year alcohol use, past month alcohol use, and so on. all the way to did you drink 5 or more drinks in the past 2 weeks? So these are our 7 indicators that we measured on the survey. We used them and we specified 5 latent classes. Of course, you've got to figure out how many classes are best, but we chose a 5-class model. And these are the item response probabilities in the matrix. And in the green bar, you can see the class membership probabilities. Of course, they sum to 100%. Our biggest class is class 5. And people in this class almost certainly have reported lifetime alcohol use, past year alcohol use, past month alcohol use, and so on. And they've really likely endorsed all 7 of these behaviors. And so then the job becomes, I'm looking at my item response probabilities. How would I label these classes? And so these are labels that we might give them. And so that 5th class I mentioned, that was the biggest class of high school seniors. We might call them heavy drinkers, for example. But our class labels are ours to make as the scientist. If we wanted to represent this model graphically, then we might draw it in as shown in the next slide. We would put our latent variables in circles and our observed variables. They might be questionnaire items, they might be data that you are drawn from health records or whatever, but we have actual observed variables and we would draw those in a box. And because the latent variable is theorized to be the reason why people respond in certain ways on our questionnaire in our observed data, the arrows go from the latent variable to the observed variables. So this would be a way we might draw a single latent class variable that is measured by 7 observed variables. Okay.
Bethany, do you want to say very briefly how LCA is different from cluster analysis?
Well, so the most similar model to cluster analysis would be latent profile analysis, which we're gonna just touch on next. In latent profile analysis, of course, our indicators are continuous. But you have this decision to make if you want to do a cluster analysis versus a latent class analysis. And in latent class analysis, you specify a model and say, I'm going to identify subgroups. I'm going to extract this many subgroups from my data. And then I'll be able to assess the fit of that model to my data. And I will have parameter estimates that reflect measurement error. With cluster analysis, it's a little bit different. You would again specify how many clusters are in your data. And but the algorithm is different. Rather than estimating measurement error, the algorithm simply organizes, think about organizing data points in multidimensional space. And you are minimizing the differences across people within a class and mathematically maximizing the distance between classes overall. And so there's an algorithm for latent class analysis that will, or for cluster analysis that will sort people in an optimized mathematical way. In latent class analysis, it's more theory driven, and it is technically a measurement model in the same way that factor analysis is a measurement model. And so we could theorize this many classes, estimate our model, and comment on model fit and interpret the measurement error. So that's a kind of a basic description of cluster analysis versus LCA. We can definitely come back to that again.
Yeah, and there should be an article on the recommended reading list in the agenda by Jay Magdison that discusses the differences between latent class analysis and cluster analysis in more detail. And Stephanie, there's another question. Could you just say a few words about any criteria to check your indicators while choosing them? So for example, correlations among items.
Yeah. And this is a great question. And this question expands when we go to LTA, and we can talk a little bit about that. So in there's the question of like data requirements, thinking about distributions and correlations. What's most important when you're fitting a latent class model is to remember what the assumptions are when we're fitting a model. And the assumptions are quite simple here. We assume that the items are independent, conditional on latent class membership. So given a latent class membership, the items are independent. That's why we don't have arrows connecting the bottom boxes to one another. We don't have these residual correlations. So what does that look like in your observed data? Well, these items actually will be correlated in your observed data. They will and they should. If they were all completely unrelated to one another, you would only have one latent class. Latent classes are specified to account for the way that these items co-occur in reality. So what I mean is, if you're fitting a latent profile model, we don't expect the raw data to be uncorrelated with each across items. We expect them to be correlated. The model posits that they would be uncorrelated within a latent class. You know, you would be looking for basic things like we wouldn't want to have a binary indicator that has one person at this level and everyone else at this level. We don't want to have super sparse data cells. So that's something we might look at. If we're fitting a latent profile model, we're making the assumption that within classes, the items are actually normally distributed. So that's a pretty strong assumption. So it's a difficult one to assess because we don't know what class people are in to look at the distributions within class. But it does imply that in overall, we should expect our items to be kind of bell-shaped. We don't want to have like a very strong ceiling or floor effect and build a latent profile model and say we're comfortable with the assumption that the items are normally distributed within classes. That is kind of a recipe for over extraction of classes due to the properties of the items. Yes, so this next question is similar. When we're looking at distributions of our indicators, our items, excuse me, we definitely, apologies. We definitely, Bethany, can you take over?
Yeah, of course. Yeah. So building off of what Stephanie just said, for the question that's in the chat, when you have questions about frequency, it depends quite a bit on how the question was asked. So if you allow a person to respond, say with the total number of drinks, that could range anywhere from 0 to, you know, whatever, more than 50. That would be technically a continuous item that could be considered for LPA. However, it's very unlikely that that item would be normally distributed within the classes. And it is, in fact, not anywhere close to being normally distributed in real life. It's often zero inflated or at the very least Poisson. And so in that case, as Stephanie said, if you break the assumption, or if the assumption is not plausible of multivariate normality within classes, you will tend to over extract and it will really change your latent class model. So in those cases, and also in cases where you have, say, an ordinal variable where you allow participants to choose 0 drinks, 1 to 2 drinks, 3 to 4 drinks, 5 or 6 drinks, and 7 or more, something like that. The ordinal models are also fit as nominal models. And so you might even need to further collapse those if there are not enough people responding to each of those categories. So the considerations for LCA versus LPA, as Stephanie said, is really dependent on that multivariate normality assumption. And then also how much information is contained at each place along that continuum. We often find that collapsing the variables into fewer categories is often helpful for model interpretation as well. Stephanie, would you like me to keep going, or how are you doing?
I think, Bethany, you were going to kind of give us a quick overview of your latent profile model of self-leader perception. So I think
Sure.
that would be great.
Yeah, I'll keep going. So latent profile analysis. So as you can probably imagine, and as Stephanie has said, the basic ideas for LPA are exactly the same as they are for LCA. We are still interested in a categorical latent construct so that individuals are divided into these subgroups. Our construct of interest is still a latent variable, and our subgroups can now be called latent classes. They can also be called latent profiles. People use different words meaning the same thing. So if you're reviewing papers or grant applications, just make sure that it's clear what they're talking about. Okay, sorry, before I go on, a response to the question above, categorical and continuous items. So that is a mixed indicator model. I can talk about that after we go through LPA. And just as with LCA, true latent class membership is unknown, but individuals belong to one and only one latent class. We just don't know which one. We have one additional set of parameters of interest in latent profile models because now we have both means and variances because our items are continuous. So we still have our latent class prevalences. So for example, if we had a latent profile called prototypical, a latent class prevalence would be the probability of membership in the prototypical latent class. But instead of item response probabilities, we now have class-specific means. So instead of having within each class the probability of responding in particular ways, now we have within each class what is the mean on the continuous indicators. So for example, if we have indicators asking how sincere do you feel you are as a leader, the mean of that sincere indicator given membership in the prototypical latent class would be the class-specific mean. Because we have means, we also have variances. And so we have class-specific variances. And in this example, it would be the variance of the sincere indicator given the prototypical latent class. The example that I'm going to talk about here very briefly is the example that's presented in the Human Performance article that's in your readings folder. And in this example, what we were looking at are latent profiles of self-leader perceptions. So we used data from introductory psychology students, about 483 of them. They were predominantly women. And we asked them a variety of questions about their self-perceptions as leaders. And then we asked them a variety of other questions about their perceptions of ideal leaders and also leader effectiveness. But for this very brief example, we're just going to talk about identifying and describing underlying latent classes of self-perceptions related to leadership among college students. So this is one example of how we might present these results, and this is analogous to the drinking example table that we just looked at, but with slightly more information because of the continuous indicators. So down the left-hand side, we have all 17 indicators that were used. So the questions were things like, how sincere are you? How compassionate are you? How knowledgeable are you? How motivated, dedicated? How pushy, manipulative, conceited are you as a leader? And in the industrial organizational psychology literature, these items are actually from a scale that sort of fits on these 4 factors of sensitivity, intelligence, dedication, and tyranny. And so that's just a heuristic to help us understand the items. And you'll see in the first column, we have the overall item means. So these were measured on a Likert scale from 1 to 10. And so this is the overall mean in the sample. So you can see that many of them are, just slightly above the midpoint of 5, except for the tyranny items, which tend to be lower. We identified 4 latent classes that we named prototypical, laissez-faire, narcissistic, and anti-prototypical, or autocratic. You can use autocratic or narcissistic here. Just below that, as we saw in the drinking table, are the sizes of the latent classes. And you can see actually that the laissez-faire leaders class is the largest with 38%, and the anti-prototypical class is the smallest. But in order to know how to label these classes and to make sense of the sizes, we have to really look at these means within the classes to understand what's going on here. So for a prototypical leader, if you study this table, what you'll notice is that the sensitivity, intelligence, and dedication items are higher than what we would expect in the overall sample, and the tyranny items are lower on average. So in the industrial organizational psychology literature, they would consider these folks to be a prototypical leader. On the opposite end of the spectrum are the anti-prototypical leaders, anti-prototypical self-perceptions. And so these folks are relatively low on sensitivity, intelligence, dedication, and relatively high on tyranny. So they're the opposite. Our laissez-faire leaders are about at the average across all of the items. And then the narcissistic self-leader perceptions, what you'll notice is they are low on sensitivity, but relatively high on intelligence and dedication, and they are actually the highest on tyranny. So with American sports seasons and American political situations, you can imagine perhaps examples of each of these types of leaders. So before I get into mixed indicator models, just want to talk a little bit about LPA model specification and selection. Both the means and variances can be held constant or be made free to vary across classes. The means, of course, are always free to vary in any models that you would probably be interested in, because that's what gives us the different interpretations of the classes. However, in order to estimate a variance for every mean in every class, that is a very high number of parameters to be estimated, and that often makes it difficult to identify the solution in terms of being confident that you found the global maximum likelihood solution. And it also can drastically change the interpretation of your classes because the variability can be different within each one. Although theoretically, we probably believe that the variance on the tyranny items are not the same for the prototypical leaders and the narcissistic leaders. Often we have to restrict those variances to be equal across the classes in order to get a stable, well-identified model. And by default, in most software packages today, including M+, those variances are held constant across classes by default. And if you want to examine other models, you need to release those restrictions. Let me just pull the chat up again. Okay, so the question is, if there are both categorical and continuous indicators, what would you recommend collapsing continuous into binary? So what I will say is how you treat your indicators is a bit of an art, as it is a science. And also, if you have truly normally distributed indicators where those indicators provide information across the entire spectrum or entire continuum on which they are measured, then I would not necessarily recommend collapsing them. In that case, I think the argument that you're quote unquote losing information is indeed a valid one. And so you can have mixed indicator models where some of the items are continuous and some of the items are categorical. Those models can be difficult to interpret because of the mixing of the scales. But I do have a paper that, if you remind me on Slack, it is not on the recommended reading list, but I do have a paper with a former student who has done this in practice. If folks are interested, I can put that reference in Slack. So you just have to be very careful about that. Now, if you have continuous items that are not normally distributed, or continuous items that are bunched up in different places. Maybe it's bimodal. You have a lot of people at the lower end of the spectrum and you have a lot of people at the higher end of the spectrum. In that case, maybe collapsing it into a binary variable makes sense. Maybe in other cases, you want to collapse it into a 3-level variable. So for example, if you have a continuous item that is, how many days on the past 30 days did you drink alcohol? Perhaps you'd want to collapse that into 0 days, 1 to 2 days, and then 3 or more days. So all of the arguments that you would typically make to collapse variables are the ones that you should think about here. So remember that they don't have to be continuous and binary. They can be continuous and categorical with multiple categories. However, you do have to pay attention to those assumptions that Stephanie was talking about earlier. And if you really truly feel that you have both continuous and categorical items, you can fit a mixed indicator model.
I would that was an excellent answer, Bethany. I agree with everything you said. I think, it's these are really critical foundational pieces, and when of any kind of model, including LTA, I think understanding the implications for your decision making is really helpful. So, for example, if you have very skewed indicators and you fit an LPA, you should understand that the likely outcome is you will get additional classes extracted that will allow the model to conform to that assumption that the items are normally distributed within class. So knowing the implications of your decision, I think, is really helpful. And yeah, I just think that I agree. The other thing I would recommend in practice is do a sensitivity analysis. I see absolutely nothing wrong with trying it with a mixed indicator model. Really get to know the results and the different number of classes. How do you interpret those classes? And then maybe go to your continuous variables, your indicators, and categorize them maybe as 3-level variables. And then rebuild your models and take a look at it empirically. Does it make sense? Can you interpret those latent classes well? I would think of that as like a sensitivity analysis.
I would too. I think that's great because you don't know at the outset, you don't necessarily know whether the constrained variances are going to affect your model more than the skewness versus, quote unquote, losing information by collapsing them. So I completely agree with the sensitivity analysis.
It's relevant to the question that was just posted as well about standardizing or mean centering items. I think it's totally fine to transform your indicators as long as you take those transformations into account when you're interpreting your latent classes. Not a problem at all. But I think having the variables with wildly different variances is a problem in LPA. And Bethany, you probably could say more about that.
Yeah, so okay, so we have a lot of questions about indicators. So I have a little bit more experience with LPA than Stephanie, so I'm gonna try to knock them off one at a time. I'm gonna follow up on the transforming one first. Transforming your indicators is completely and totally fine. And remember that the reason that we would transform an indicator is to help it conform more to that normality assumption. When you go to interpret that model, often you would want to back transform those indicators so that they're on the original metric solely for the interpretation. This also is related to another point that I wanted to make, which is many of us are probably more familiar with regression modeling. And remember that you have to check the distribution of your outcome variable in linear regression, right? Or logistic regression, or whatever kind of regression you want to do. And if your outcome does not conform to the assumptions being made, then you have to transform it. Maybe you have to collapse it. Maybe you have to try a log transformation or some other transformation. So those ideas are analogous to assessing your indicators here. Z-scores, different scales. I completely agree with Stephanie. Theoretically, the scales of different items should not make a difference. In practical terms and in real life, they do. If you have a number of items with very small variances combined with a bunch of items with very large variances, or items that are on, say, a 0 to 5 scale and other items that are on a 0 to 100 scale, practically speaking, it does affect the model's ability to identify the maximum likelihood estimates, so both convergence and identification. So if you have fairly small differences in the scales, like 0 to 10 and 0 to 20 with relatively similar variances, in my experience, that's okay. But if they're wildly different, you would want to do something different. Now, z-scores is an interesting example. That would be one option for sure if you have very different scales or very different variances. The issue, though, is that you have to be very careful in the interpretation of the classes, because the classes are no longer high or low on average in those classes. It's higher than average or lower than average within each class. So if you were to fit that model with different subsamples, it's going to center those indicators in different places, or if you're trying to harmonize across data sets. So whatever you do to your indicators, whether it's transforming to make it more normal or transforming it to have a constant scale, you just need to remember all of those things when you go to interpret the models, and note that they can have quite different interpretations. Rules of thumb as far as the minimum and maximum overall prevalence of binary indicators. It really depends on the purpose of the analysis. So the reality is that if all of your indicators all have super high and super low probabilities of endorsement, like above 80% or below 10%, those items may or may not work well at identifying and interpreting your classes. So, however, if you have a set of items that you want to investigate how they work together to identify classes, then maybe you want to fit the model with all of those. And the ones with high prevalences or very low prevalences might not contribute much information, but now you would know how they work in concert with the other items. So it's, and as Stephanie said, a sensitivity analysis is always a good thing to do if you have questions about particular indicators or different coding. But again, items that, have 90% or more endorsement or less than 10% endorsement, sometimes that they don't provide a ton of information. In contrast, let's say that we have a national sample in the United States, and one of those indicators is about cocaine use. Cocaine use in the general population might have a very low prevalence, but it might have a comparably high prevalence in, say, a generalist drug users class. So it's a little bit of a theoretical question and a little bit of an empirical question about how those indicators operate in the analysis. LPA, where there are different numbers on the Likert scales. Yeah, 4 versus 5-point scales. Yes, you can. And generally, in my experience, they're not so different or have such different variances that you could not put them in the same model. Generally, if you have 4, 5, 6-point Likert scales, technically speaking, it will work okay. However, it can be very confusing to the reader. If you have an average of 3.0 within a class on a 4-point scale versus a 6-point scale, that could have very different implications. And so one thing that I like to do to provide just a little bit of extra information to the reader is that column in the previous slides about the overall item mean in the sample can provide a quick heuristic of for comparison, but you do want to make sure that your reader doesn't get confused about that. If we use indicators on different scales, what should the y-axis in graphs represent? There wouldn't be anything different here than any other analysis that you would do. It depends on how you would want to plot them together. you would either need to put them in different graphs, or you would have a very big y-axis, and perhaps you could have a line across it at the different means for the items. Or sorry, you could have the item mean marked for each item.
Yeah, and I think it'd be reasonable in that case to just do a table the way Bethany presented her means for each class. And so you could look at them and interpret them without having to graph them with really different axes. Yeah.
Yep, I totally agree with Stephanie's question. In the context of longitudinal data, how you would center variables on a z-score is an open question. For those of you interested in random effects models, also interesting question there. When there's an age dependency in the variables, covariate effects. Okay, so Anne, I think we might save your question for when we talk about measurement invariance, because there are a couple of different questions that you're asking there. Let's take the one that's relevant to LPA, which is checking for grouping or covariate effects in your LPA. So this is a fairly standard response that I'm going to give. In LCA and LPA, it depends on the previous research, theory, and your knowledge of what is going on in the data. So for example, perhaps at the outset, you do not suspect that there is any reason to think that people who have depression and people who don't have depression have measurement differences in positive and negative affect. I'm just making this up. Let's just say that you don't start off with any ideas about differences in groups. Then you need to be careful about testing a lot of different types of measurement invariance, because that's a lot of statistical tests, and you can find spurious differences that are not actually differences in the measurement model. If instead you're thinking about maybe, say, delinquency, and there's all this previous theoretical work and empirical work showing that boys and girls manifest delinquency differently at different ages along the developmental spectrum. In that case, you probably have reason to suspect from the outset that your classes might not be similar in terms of their measurement. And in that case, you could start by analyzing boys and girls separately, or by analyzing them together and then testing measurement invariance later. For ages, let's say you have a very, very large age range. Like, let's say you have ages 16 to 60 in some national data set, and you want to investigate whether or not the classes that you identified in drinking are the same across that entire spectrum. Then it would be good to probably chunk up your ages, perhaps based on developmental milestones or decades, so that you can investigate measurement invariance across that whole age spectrum to ensure that your classes have the same interpretation. If you want to just look at how age is related to class membership, then you could put it in as a covariate, but you cannot explicitly test measurement invariance with a covariate. In LTA, the idea of age dependency can be a little bit different. Perhaps with LTA, you have an age range from 12 to 18, and then you follow those individuals every 6 months for 2 years. In that case, you would want to test for measurement invariance across time to make sure that your latent classes have the same interpretation across all of your panels. And we'll talk about measurement invariance across time in a lot more detail. So hopefully that's okay as a temporary answer. If anybody has a follow-up and want to stick it in there real quick, otherwise we will talk much more about age-dependent measurement invariance later this afternoon.
This is great. These are foundational issues, so it is worth us spending time this morning, I think, talking about these issues. The next 3 slides that Bethany's going to go through talk about latent class homogeneity, how similar people are within classes, different across classes. How similar they are within a class. Latent class separation, which is how distinct the classes are from one another. And then just a note, again, looping back on some of the only key assumptions of these models. These are foundational concepts before we even talk about LTA, which will be the next segment. The issues that are coming up here, if I'm kind of tracking them correctly, these are important questions about how do I select indicators at a certain time point? How do I code or transform them at a certain time point? How do I think about sparseness or assess variability on each indicator that I'm including in my model? Um, so when you're making these difficult decisions, it's kind of confounded. Sorry, the complexities increase when you go to LTA and more things that you have to consider, like is the exact set of indicators at time one perfectly relevant and assessed the same way and mean the same thing at the subsequent time. So these issues are going to be really critical to nail down at a particular time point that we're talking about now before we go to latent transition analysis. One thing I want to say is that these issues that we're talking about, they're so foundational. Because what you put into the model exactly is indicating the latent construct that you're trying to measure. So if you're putting in the wrong stuff, you're not measuring the latent construct you want to measure. You've got to get the right information into the model. The other thing I want to just comment on is all of these issues are going to affect statistical power. And power is a tricky thing in these models. And we can talk a little bit about statistical power. You know, when I'm thinking now about statistical power, I'm thinking about like, how do I make sure I have enough people, say, in the analysis, but then that I need to have items that measure my construct well enough to be able to detect my underlying construct. So issues of statistical power are tricky. We can talk a little bit about that later. We're going to say this throughout today and tomorrow a number of times. So these decisions are it's going to come back to how well are you able to measure your latent construct at all with the data you have at hand. If you're able to identify a set of indicators that tap into that construct really pretty neatly, then your power is going to be stronger and you can get away with a lot of more things. If you don't have easy measurement of that construct, and it's going to be related to these two slides that Bethany's going to go over. If you don't have really solid measurement, which is totally fine, a lot of constructs are just harder to measure. You can't get away with as much. Like sparse indicators are going to be more problematic. Anyway, these issues are all like foundational. And then as we move to LTA, it's really important to think about all of these ideas. And when we move to multiple time points, as like something Bethany sort of alluded to, or similarly is, you know, one of your indicators, if you have a binary indicator for an extreme behavior, maybe at time one, essentially no one's doing it, but it's critical behavior. And at time two, you know that you have a lot of people reporting that behavior. And so you want to keep that in your model. So these are complicated decisions that we make. I'll stop there.
Yeah.
Bethany, let's talk through these concepts. I think they're really relevant.
Yeah. So two sort of heuristics that we use to evaluate the quality of latent classes are latent class homogeneity and latent class separation. In general, homogeneity has to do with the quality of your measurement model. And it's getting at the degree to which individuals within classes are similar to one another. So in LCA, high homogeneity in a class can be indicated by item response probabilities close to 0 and 1. That's because what that is indicating is that among people who are in that class, they have a very, very high or very, very low probability of answering in a particular way to that item. So for example, in our drinking example, the heavy episodic or binge drinking indicator, if it has a 0.98%, 0.98 or 98% chance of answering yes to that item has high homogeneity within that class. And so it indicates the strength of the measurement of that class. Not in general, but values closer to 0 and 1 are preferred. In LPA, however, with our continuous items, especially continuous items that are on different scales, there is no particular value that indicates high quality measurement because the mean could be anywhere in the range of that scale. So in LPA, high homogeneity in a class is indicated by small item variances, meaning that among people in that class or profile, there isn't a lot of variability in their average value. However, as I said earlier, those variances often have to be constrained to be equal across the classes in order to get the model to estimate well. And so if your variances are constrained to be equal across the classes, then there's no difference in the classes in the variability, meaning they all have the same more or less amount of measurement quality. So homogeneity is more difficult to assess in LPA than it is in LCA. The idea of latent class separation, however, is equally applicable in both cases. Separation is the degree to which the latent classes can clearly be distinguished from each other, so they have unique interpretations. And separation, we look at class-specific probabilities and means and the class interpretations. So if we have 5 classes and 2 of them have pretty similar interpretations, then you would want to look at some of your other models to see if you have quote unquote over-extracted and 2 of the classes are nearly the same and that a smaller model would be more appropriate. So again, homogeneity has to do with the quality of the measurement and separation has to do with the unique interpretability of all of the identified classes or profiles. Stephanie talked a lot about our key assumptions earlier, but just as a reminder for when you want to look back at this, conditional independence means that the latent class indicators are independent within the classes. Remember, that does not mean that we think the indicators are unrelated prior to modeling. In fact, your items might have, relatively high correlations, or at least are moderately correlated because you want to be able to see patterns. This is after we know what class you belong to, then the indicators are independent. In LPA, of course, we've talked a lot about that critical assumption that the indicators are normally distributed within classes. If this assumption is violated, simulation studies suggest that you will over-extract the number of classes. So you have to be very careful with skewed indicators in particular, or indicators that have some sort of multimodal distribution.
So we're going to talk about a conceptual introduction to LTA, talk through the parameters that are estimated, and we're going to look at an example in the context of adolescent depression across 2 time points. Okay, so let's start with a graphical representation. So just extending the way we would draw a latent class model, we might draw a latent transition model as you see it here, with the idea that there's a latent class variable at one time point, and people can change their class membership over time. And so there's the same latent class variable at a second time point. So we're going to be kind of grounding this workshop in the traditional LTA model, where you would name the latent construct the same thing at time 1 and at time 2. And yes, you can have 3 or more time points, which we'll touch on tomorrow. But we're going to talk today, we're going to stick to a 2-time model, same latent class variable, and same indicators, the exact same indicators over time. Can you specify a model in M+ that has different indicators? Sure. Does that allow you to estimate change over time in a single construct that has the same meaning over time? No. So we're going to start with this classic example, same indicators, X1, X2, and so on. and you have measured them at time 1 and you've measured them at time 2.
Great.
Okay, great. So let's so just a reminder, like when we say LTA, what are we actually talking about? So LTA, as we're talking about it today and tomorrow, is a straightforward longitudinal extension of LCA. So we assume that I'm going to assume that today, for the purpose of this argument, that the unit of analysis is the individual, people, and we would think that people change over time. So development, change over time, in this case, can be represented as movement through discrete stages or categories. So you're in this class at time 1 and this class at time 2, or maybe you're in the same latent class at time 1 and time 2. We assume that there's measurement error associated with the measurement of these discrete categories or stages, right? That's why we have a latent class model, measurement model at time 1. We have a latent class measurement model at time 2. There's measurement error associated with what class they're in. And we assume, of course, that there's heterogeneity at time 1 and what class they're in. And given where you are at time 1, there's heterogeneity in how you may or may not transition to another class over time. And it's this heterogeneity and movement from class 1, from your latent class at time 1 to your latent class at time 2. That's the purpose of LTA. Okay, so so one way to think about it is it's a way you can estimate and test models of stage sequential development. That's one way that it's historically been talked about. I think the main point here is if we think that class membership can change over time, and we have data from the same individuals over time, then we are in sort of LTA territory. Just a quick note that's italicized here. Historically in the literature, you will see that sometimes the literature will talk about latent statuses and latent status membership over time. It is exactly the same thing. We're going to stick with the latent class language here, but sometimes people will flip to that label latent statuses for latent classes that are measured over time. It's the same thing, it's just a semantics thing. Okay, so in LTA, the purpose is to estimate the prevalence of, that's a leftover here language, latent classes. So the prevalence of latent classes at a certain time point, or latent statuses at a certain time point. And we're also now estimating the incidence of transitions between latent classes over time, all while adjusting for measurement error. So in addition to looking at the measurement model itself and estimating the class membership probabilities, now we're adding a third set of parameters called transition probabilities. These are, for example, the probability of membership in the depressed latent class at time 2, conditional on membership in the sad and disliked class at time 1. So what is the probability that someone goes from this class at time 1 to this class at time 2? So hopefully you're already getting the sense, based on the interpretation, that these transition probabilities are conditional probabilities. So we'll see that a little bit more in the example.